Hi everyone! Today we're going to be talking about the base E and natural logs. Our objectives for today are that students will be able to evaluate expressions involving the natural base and natural logarithm, and you'll be able to solve exponential equations using natural logarithms. Let's get started. So what exactly is E? E is an irrational number. All right, so let's write that down. So it's an irrational number just like pi. All right, we've got E as well. Irrational numbers go on forever. They have no end. And the approximate value of E is 2.71828. And it goes on forever and ever and ever. All right, so we know like pi is 3.14. Well, E is 2.718. All right, so E often occurs as the base of exponential and logarithmic functions that describe real-world scenarios. The base E exponential functions, all right, so exponential functions with the base E are called natural base exponential functions. An example of this would be the function f of x equals e to the x power. This is a natural base exponential function. Now, base E logarithmic functions are called natural logarithms. All right, so we use the term natural logarithms to describe logarithms that have a base E. Just like we learned before, common logarithms have a base of 10. Natural logarithms have a base E. So for example, anytime we have a log, all right, a logarithmic function, that's f of x equals log base E of x. This is a base E or a natural logarithm. We often just abbreviate it as f of x equals ln x. And this is what you will more commonly see. So anytime you see f of x equals ln x, this is the natural logarithm. It's just a logarithm with base E. And I looked this up because I wasn't exactly sure, why do we use ln for natural logarithm? Why wouldn't it be nl? All right, and the reason it is ln is because the Latin name for the natural log is Logarithmus naturale, so that gives it the abbreviation LN. All right, so it stems from the Latin term Logarithmus naturale, and I'm not even sure I'm pronouncing that right, all right? But you will always see it abbreviated as f of x equals ln x, and that just means a logarithm with base E. All right, so if we're converting between forms, so for numbers 1 through 3, we're going to write each equation in logarithmic form. So we want to do the same thing we were doing before when we had common logs and log bases of different numbers. All right, it doesn't matter. We're still going to do the little L trick to help us convert it from exponential form into logarithmic form. So we would say log base E of 24 equals x. So log base E of 24 equals x. And anytime we've got log base E, we want to rewrite this as natural log of 24 equals x. And that would be our final answer. We converted it from exponential form into logarithmic form, and because it's base E, we rewrite it as ln 24, or natural log of 24. All right, number 2, it's the same idea. So log base E of x equals 9. Log base E of x equals 9. We've got log base E, so we rewrite this as natural log of x equals 9. And that's our final answer. We converted it to logarithmic form. Number 3, we would say log base E of 72 equals x plus 5. So log base E of 72 equals x plus 5. And log base E, we rewrite this as natural log of 72 equals x plus 5. And we've converted it. Now, if we're writing each equation in exponential form, so we're writing this natural log of x equals 58. So anytime we have natural log of x, it's the same thing. Natural log of x is the same thing as log base E of x equals 58. So we do the e trick. E to the 58th power equals x. E to the 58th power equals x. So our base to the 58th power equals x. Our base is e. All right, so for number 5, it's the same idea. We've got a base of e. So then we would say e to the x power equals 6. E to the x power equals 6. Natural log has a base of e. So e to the 32 power equals x plus 9. Or x minus 9. And that's our final answer. All right, now all of the same properties of logarithms that we learned with common logs apply to natural logarithms, all right? So it's the same ideas. So we can still use the product property, quotient property, and power property with natural logs as well. So if we have natural log of 3 plus natural log of 16, it's the same thing as the natural log of 3 times 16. So 3 times 16 gives us 48. So we condense it to be the natural log of 48. Number 8. First thing we want to do is our power rule. When we're condensing, we take the 2, bring it up. So we get natural log of 63 minus natural log of 3 squared. Natural log of 63 minus natural log of 9. Then we can use the quotient property. We can say natural log of 63 divided by 9. And then we're going to get natural log of 7. All right, and then number 9, same idea. We want to use our power rule first. All right, all the same properties of common logs apply to natural logs as well. So we get the natural log of 64 to the 1/3 power plus the natural log of x squared. All right, and 64 to the 1/3 power is the same thing as the cube root of 64. The cube root of 64 is 4. So we would rewrite this as natural log of 4 plus natural log of x squared. Now we can use product rule to condense this. And we would say ln of 4x squared, or natural log of 4x squared. All right, and then if we want to expand, it's the same idea. We're just using the product property again. Just like common logs, same thing with natural logs. So this is 5 times x, so we would rewrite this as natural log of 5 plus the natural log of x. All right, so looking at number 11, first thing we want to do is distribute the squared. So we want to take this squared and apply it to the a to the 3rd and to the b. So we rewrite this as ln of a to the 6th over b squared. Then we want to rewrite this using quotient rule. So we would rewrite this as ln of a to the 6th minus ln b squared. All right, and anytime I say ln, I'm referring to natural log. All right, then we want to use power rule and bring down the 6, power rule, bring down the 2. So we end up with 6 times the natural log of a minus 2 times the natural log of b. And that would be our final expanded logarithm. Number 12, all right? Now we want to rewrite this first in exponential form. So we've got natural log of m squared n to the 1/3 power, all right? Then we want to distribute the 1/3 to both terms inside the parentheses, so we get ln m to the 2/3 n to the 1/3. Then we want to break this apart using the power rule. So we've got natural log of m to the 2/3 plus natural log of n to the 1/3. Then power rule, bring it down. Power rule, bring it down. We end up with 2/3 times the natural log of m plus 1/3 natural log of n. And that would be our final expanded natural logarithm. All right, now we want to solve equations that involve natural logarithms. So we always want to solve the equation and be sure to check for extraneous solutions, because remember, we cannot have negative logarithms and we can't have negative natural logarithms either. All right, so first thing we want to do, if we had a logarithm with the same base, right? If we had log base e or if we had log base 3 and log base 3, we would set these equal to each other. So the same thing happens when we have the same base in front. They're both log base e and log base e, or natural log, natural log. So what we can do is set 4x minus 27 equal to 15 minus 2x. Now we're just solving for x. So add 2x to both sides, add 27. These will cancel out. We're left with 6x equals 42. Divide by 6, x equals 7. Now to check for extraneous solutions, what you would want to do is take 7 and go back and plug it in. So 4 times 7 minus 27 is going to give you positive 1. That is not a negative logarithm, so you're good. It's a positive. It would be a natural log of 1. That's positive. Now 15 minus 2 times 7 would give you, 15 minus 14 would give you 1. All right, so these are equivalent and they're both positive. Therefore, x equals 7 is not an extraneous solution. It is a valid solution. We checked for extraneous solutions and we're good. X equals 7 is our final answer. All right, number 15. We need to condense both sides of the equal sign into a single natural logarithm before we can set them equal to each other, before we can take the logarithm of both sides and drop the n of the ln. All right, so the left side of the equation, we've got ln of 72 minus ln of 4. So we would condense this natural log of 72 divided by 4 equals. Over here, we've got the natural log of 6 plus the natural log of a minus 2. So we would condense this to be natural log of 6 times a minus 2. All right, then on this side, or we can say ln, 72 divided by 4 is going to give us 18 equals natural log of 6a minus 12. Now they both have a natural log in front, so we can cancel them out and set 18 equal to 6a minus 12. Add 12 to both sides. Those will cancel out. We're left with 30 equals 6a. Divide both sides by 6, and a equals 5. Then you have to go back and check for extraneous solutions. So we look, where can we plug in a? We can plug it in here. So if we plug 5 in, we would get the natural log of 5 minus 2, which would give us the natural log of 3. 3 is positive. It is not negative. So we are good. We do not have any extraneous solutions. A equals 5 is our final answer. All right, 17. We've got a logarithm equals a number. So when we're solving these equations, what we would want to do is convert it from logarithmic form to exponential form. We know that natural logs have a base of e, and then we would use our little e trick to convert it to exponential form. So we would say e to the second power equals 8x. So e to the second power equals 8x. Now, you should have an E button in your calculator. So if you can't find it, raise your hand and call me over so I can help you. But look for that E button in your calculator, and then you would want to say e to the second power equals, and you're going to get a decimal. So when you plug e squared into your calculator, you should get 7.3891, and just round to 4 decimal places. All right, I just want 4 decimal places. And that equals 8x. Then you're going to divide both sides by 8, and you're going to get that x equals 0.9236. And that is your solution. X equals 0.09236. And if you were to take this and plug it back in, you would get 8 times this decimal, and it would give you a positive answer. So you know that it is not extraneous. It is a valid solution. All right, so problem 19. When it's in exponential form and we know that we can't have common bases, we want to take the log of both sides in order to solve this equation. Now, when we've got an exponential function with base e, we want to take the natural log of both sides. So, we throw an ln in front of both sides of the equation. So we got natural log of e to the x equals natural log of 57. Now, something that you should write down and you need to remember is that anytime you have ln of e, this equals 1. Because ln base e of e, so anytime you have something that says ln of e, it's always going to equal 1. So if we were to use the power rule and bring this x down, we would be saying x times ln of e equals ln of 57. All right, if you were to plug ln of e in your calculator, you would get 1. So the easiest thing to remember is just memorize that ln of e equals 1 because natural log is the inverse of e. So when we take the inverse of something, it equals 1, right? If we were to do 2 over 1 times 1/2, their inverses, we get 1. Same thing with natural log and e. The inverse of e is natural log, so it's always going to equal 1. So ln of e equals 1. So x times 1 equals ln of 57, or natural log of 57. So x equals natural log of 57. So basically, anytime you see this right here, ln of e to the x power, you can just cancel out the ln of e and bring whatever is your power down. So it just becomes x. So we can rewrite ln of e to the x power. Ln of e cancels out and just rewrite it as x equals the other side of the equal sign. All right, but this was why we can do that. Then you're going to plug in natural log of 57 into your calculator. And if you haven't found the natural log button, raise your hand so I can call you over, or so you can call me over and I'll help you find it. So x equals natural log of 57, which is going to give us 4.0431. And that's our final answer. All right, last but not least, number 21. All right, we've got 5 times e to the 4n power equals 95. All right, and anytime we've got an exponential function with base e, we want to solve it just like we did number 19, but we've got to get that exponential function, or that base e, all by itself. So the first thing we want to do is divide both sides by 5 to get that e by itself. So 5s will cancel out over here. We're left with e to the 4n power equals, and 95 divided by 5 is going to give us 19. Then we want to take the natural log of both sides. So we throw natural log in front here, natural log in front here. So we end up with natural log of e to the 4n power equals natural log of 19. We know natural log of e equals 1, and we bring that 4n down by using the power property. So ln of e cancels out. We're left with 4n equals ln of 19. Divide by 4, and we plug this into our calculator. You would want to plug in ln of 19, or natural log of 19, divided by 4, and you're going to get that n equals 0.7361. And that's our final answer. All right, so I hope you learned a thing or two about base e and natural logarithms today. Please look to your teacher or look to the board to see what to do next, and I hope that you have a great day.